Hello, everybody. Today we're going to talk about a really fundamental idea around web scale architectures, and that's the idea that we need different application architectures to support them, and that those application architectures go a long way to making some things possible for us, as well as precluding other options that perhaps we might be interested in. So today we're going to look at those different architectures and kind of quickly skim through them and why you'd want to do those different architectures. So deployment architecture. So what this is talking about is how do you build the resources available to support an application? Well, the big idea behind this is that the architecture should match the workload. So different applications generate different workloads. A web serving application is going to generate a different workload than a database architecture. An analytics application is going to be different than let's see, I'm trying to think of some sort of a gaming application. Those are just different. Well, we've got lots of options available to us, starting from mainframes. Mainframes are really nice machines for certain workloads. Primarily, the good thing about mainframes is that they support database workloads so well. They're so good at handling large numbers of database updates throughout the day. They're just great at that. Would you use them as a web serving architecture? Well, you could, but perhaps it's not, that may not be their primary strength. The other great thing about mainframes, as I'm sure you've heard from Professor Hill, is how reliable they are. The mainframes are awesome. You can replace a power supply. Well, the darn thing is still working in production. Just that kind of spectacular stuff. The bad points about mainframes, is that they're very expensive and that there's a very small number of manufacturers that actually make mainframes of the quality that companies are looking for. Now, that said, the main workload that mainframes support are, financial transactions and database transactions. So a transaction-oriented application is great for mainframes. So you'll see things like banks and insurance companies. They'll have a fleet of a dozen mainframes that all work handling their customer database, their main production environment. They're awesome for that. You have lots of people working on them at the same time. You have lots of different connections coming in. Awesome. Another kind of a workload, application architecture, are monolithic servers. And you deployed one of these as part of your Lab 1. So single server, vertically scaled. So what that means is that we've got a single machine that's going to handle this application workload, and to scale it. So if our application needs more resources, what do? We add more resources to our one single server. So we add more RAM, add more disks, add more network connectivity. But of course, the problem is that you can only add so much, and then you're going to be limited to the production capabilities that you can support. So monolithic servers are good, except they create one single point of failure. They're very difficult to manage the applications that reside on a monolithic server because it's hard to see what the problem is. You've got so much going on one server, and one part may be generating some sort of errors or something, but it's hard to tell where that part of the application comes from because there's so much involved with what's going on in these guys. The other thing is that they're prone to server sprawl. What that means is that when you have One, you want to deploy another application, you need another server. And maybe that application hits and sticks around, maybe it doesn't. But when do you pull that hardware resource out? That it's sometimes these hardware resources will stick around and the application won't be used at all, but nobody gets around to pulling the resources back. So primary workload, medium-sized application services, it's a good workload for this. Now, the other thing that monolithic servers support really well are ad hoc application development. So if you want to try something out, it's easy to just bundle all of the services that you need for that application onto one single server, and then see how it works. If it works well, then you can pull it off of that single server and refactor it into a multi service application. So the two basics, mainframes and monolithics. Now, virtual machines, we love virtual machines. They were the thing that broke us away from our server sprawl, where we had back in the day, data centers were expanding like crazy and they're taking over office space all around them. Virtualization came around, and all of a sudden we were able to take all those machines that used to exist as single pieces of hardware, and we could combine them, we could collapse them onto a single server with lots of virtual machines. That was great. The problem is that it still creates a single point of failure, in that if that single server fails, you lose lots of different application services at the same time. So lots of neat stuff about it. I mean, look at Arliss. Arliss is an awesome little private cloud where you guys run virtual machines on it. We manage all the resources of Arliss as a single pool. So even though each machine may not have tons of RAM on it, we can allocate bunches of RAM from multiple machines to support one virtual machine. It's awesome. Uh, Virtual machines, we can scale them vertically or horizontally. We can allocate more resources to single virtual machines, or more, or we can deploy a whole bunch of smaller virtual machines horizontally. Uh, the small number of hypervisor vendors is both a positive and a negative, in that right now nobody talks about the different hypervisor vendors that support their private cloud. But if there was a hack that allowed bad guys to go from one virtual machine to another, that's called a hyperjacking hack, then what would happen is that would apply to only one vendor to begin with, and then maybe others later. And then all of a sudden, everybody would want to know which hypervisor vendor you're using in your private cloud. So, we know all about VMware, we know about Zen, we know about some of the other hypervisor vendors out there, and there's a small number of those, but it's really interesting. In a virtualized environment, every virtual machine represents an entire operating system. So if you've got 10 virtual machines running on one physical machine, you've got 10 network operating stacks that are running, one for each one of your virtual machines. That's, that's nice, I guess, but it also represents a tremendous amount of waste. And when we start talking about Docker containers, we'll look at that and we'll say, well, here we've got one network operating system stack that supports all of the different containers. So, that's an issue. It's well-known architecture. We've been dealing with virtual machines for a long time. Virtual machines started out in a mainframe environment, and it was kind of like the first time they got a mainframe to work, they looked at it and said, let's do that again. And virtual machines were born. So we've got lots of different administrative tools and options available to us, mostly because it's been around for a while. People have developed the tooling to support this. And our primary workload for virtual machines are usually horizontally scaled workloads, flexible architectures, server consolidation, take lots of underused physical servers and consolidate them together onto one uh, virtual machine server. So, very positive, nice to use. You guys use them on RLS, all good. Docker containers. This is another deployment architecture that is very popular these days, and not as well understood as other architectures are. What's the difference between Docker containers and virtual machines? Well, each container represents only a portion of the overall operating system. So shared parts of the operating system, and it shares parts of the operating system with the host computer. So each container only contains the executables that it absolutely needs to contain to run the application that's running on that particular container. Other parts of the operating system are shared with the host computer. So back to our network stack again. That network stack is shared by all of the containers on a Docker server, um, by all the containers that run on there. Not each one of the containers that run on that Docker server don't have their own network operating stack. They share the main host machine's operating stack, uh, network stack, with all the other containers. So it's a really interesting way to run things. Uh, it's it's a much less well understood architecture. People have a tough time figuring out how to do it. The tricky parts of Docker deployments are things like the um, the the sharing of the operating system, because that means that you've only got one IP address assigned to the host machine, and all of the containers that reside on that host machine either need to share that IP address or have a separate one associated with them, and that's a little trickier thing to do. The other thing is that because Docker containers come and go so quickly because they're so small, is that persistent storage is a problem. Docker containers are not built around the idea of persistence. They're not meant to last for a long time. They're meant to be used and then turned off, and other versions swapped into place for them. Well, how do you deal with storage in that world? Persistent storage is hard to provide in a Docker container. Now, you could use another network storage machine, and that's it, so it's doable, but it just gets tricky. It's a fairly new architecture, although containers have been around for a long time. The thing that makes Docker containers different from other containers like LXC, Rocket, and some of the others is that Docker consists not only of the containers, but all of the operating the services around those Docker containers that you need to support the use of those Docker containers. Everything from Docker D to the way that you can store Docker containers on Docker. So all of that stuff comes together around Docker containers to make for a more useful architecture. Now, one of the really neat things about Docker containers is because they're so small, they're not designed to persist, you can create immutable architectures. So wouldn't it be a neat way to prevent people from hacking our systems if we could make it so those systems could never change? That's an immutable architecture. And the reason we can do immutable architectures with Docker containers is that just like in your last lab, rather than change the files that you're serving off of your your web servers in the last lab, what you're going to do is you're just going to get rid of when you have a new version of your web files to serve, you're going to get rid of the servers that were serving the old version and bring in new versions of the servers that are going to serve the new stuff. So that's an immutable architecture. And the neat thing about that is that not only can't, the reason why the bad guys can't change them is because we can't either. So immutable architectures are really nice. Horizontally scaling, we can create big fleets of containers that we can have come and go, deploy services, and then delete the services through and instantiate new services through our load balancers. There's just a lot of flexibility that we can bring to play with Docker containers. So primary workload for Docker containers are non-persistent storage or processing head ends for other services, web servers, horizontally scaled workloads, those kind of things. That's what Docker containers are made for. Are they going to run your customer database? Probably not. That's going to be for systems that have access to persistent storage, that are vertically scaled, that are designed to stick around for the long run. That's not Docker's thing. Docker's thing are these non-persistent, highly highly changeable architectures that we use for just small parts of our application architectures. Serverless computing. This is a new one that's really coming online and is very popular. Mostly cloud-based, although you certainly could do this on a private cloud. I should have said mostly public cloud-based, but certainly could be done as a private cloud. It creates a function as a service architecture. So, in cloud computing, we've got infrastructure as a service, application as a service, and then whatever the last one is. But this is function as a service, and function as a service is really cool. What happens is you build your applications so they exist out there as just a function. And when your function gets called, your function runs to completion and then goes away again. So think about using serverless computing for things like web servers that aren't used very much, so that you don't want them sitting out there spinning as a full server just waiting for that connection that very seldom comes. If you set them up as a serverless computing, they exist out there as a function that's pretty much turned off until a request comes in. Then the function wakes up, does its thing, and shuts down again. So, really interesting stuff. Alexa, if you've got smart speakers. Oh, mine just turned on. That didn't say anything. And other less used web workloads. That turns out to be a really important field and type of a workload. So application architectures, this is the big distinction, monolithic versus microservices. Monolithic, we've got one big cake, everybody gets a piece of the cake. Microservices, we've got this object called cake, but the object called cake is really made up of lots of small cakes. So everybody gets their own cake. And there's no fingers into the frosting that crosses from one cake to the other. Ooh, gross, right? So, it's just kind of a silly way to describe it. But monolithic versus microservice, that's where we're really heading for. Now, where does all this come from? Well, it comes from an evolutionary path that is still evolving. This one ends at 2014, and it doesn't have serverless on it. It should have serverless. But It starts out with monolithic architectures in the 1970s. Those were great days for system administrators because you only had one set of um, uh, processors to support, and everybody just had green screens that didn't do any processing. So it was easy. But then we add on, and what happens is we take our big applications and we break them up into multiple smaller applications. Originally, we would have a UX, a business logic layer, and then a data layer. Then now we're breaking that up even more and more, and we're doing all kinds of much more interesting things with our applications. So so here's a monolithic application architecture. We've got all these users that are logging in, and they're going to hit this monolithic application that's one single server, and it's got everything on board. Problem that we have with this is that it's very inflexible. Doesn't scale up, doesn't scale down. If our application starts out as not very popular, then it gets more popular. We can add more resources to the server, but there's a real limit to how far we can go. And it's very hard to tell if you're having poor performance from your single server architecture. It's hard to tell what part of the single server uh, uh, application architecture is the source of the problem. It's really hard to manage. And it's hard to access the individual components to use in other applications. If you have a database that you want to use for multiple applications, it's hard to do that in a monolithic architecture. Now, along comes multi-tiered architectures, and this is, kind of a classic way to break things up. So we've got our web browsers out there, our users out there, and they access a web tier. And in that web tier, we have web servers that accepting incoming connections, do the processing, break the incoming connection down into a bunch of queries, or break them down so that they can go to an application layer where we have our business logic, and that business logic takes those incoming queries, breaks them up into incoming requests, breaks them up into queries that we then issue against multiple databases, because most big applications have multiple databases behind them. And resolving one request is hard to do in one database. You've got several. If you think about like a web video browsing service, you've got a customer database, you've got a database of videos available to watch, you've got I don't know, a bunch of different parts to that. And so you've got your database servers in the back end. There's usually several of those. You've got application servers in a business logic tier, and then you got your web servers. Request comes in from the web server. I'll try it again. Request comes in from the web server. It gets reformatted and sent on to the business logic server, which breaks it up into a number of queries that go against our multiple databases. The multiple databases respond to those queries. The application server receives the responses from those database servers, multiple database servers, collapses all that information together, forwards it back out to the web server, which takes all that raw data and puts it into a easy to work with format, makes it pretty, and forwards it on to our web browsers. And that's how multi-tiered architecture works. And it's a big step forward because you can handle a much bigger workload if you offload parts of the hard stuff to machines like web servers. That can be things like the endpoint for incoming connections. We can load balance across them. We can do all kinds of stuff with them, and without making our back end much more important, servers be responsible for this incredible workload. So Individual components can be utilized by different applications. So if we've got one database that's like a customer database, if we've got multiple applications, they can all use the one customer database. If we had a website, we started a business called cats.com. We created a database to support that. We created a web page to support that. We created a business logic tier, all that kind of stuff. Built it to support cats.com. Well, what happens if someday we decided, hey, why don't we build a dogs.com? Well, we could use all the same resources that we've already built. All the database part, the business logic part. The only thing we would have to do would be to come up with a different web page. And so anybody who spends some money building a cats.com has a tremendous business advantage over somebody else who says, I want to start dogs.com. Why? You've already built most of the components. So that's a big deal. So multi-tiered architectures usually consist of small services connected via APIs. Each one of those small services can be managed separately, and each component, each one of those small services, again, can be scaled separately, either up or down. This is the way something like Facebook works, where you've got this MySQL application that's nothing but a big database. But rather than run it as a monolithic database, which would be one database to support all of your users, you break it up in a process called sharding, where you look at the different user groups that you have and break them into small groups and then serve those database files from database servers that are closer to the users that are interacting, that are in that shard. Also, do things like, if you notice the Messenger application, that's a totally separate application from the regular Facebook.com application. It's got some connectivity between them, but largely it's on its own. Now, the part that's common between them are things like authentication issues, so that when somebody logs in to Facebook or Messenger, you're using the same authentication engines to make sure that they know who you are. So having that authentication engine built to support Facebook meant that Messenger didn't have to build it. It could just use what already exists. It already existed. And that allowed them to build Messenger at a really competitive pricing point to make it so that that application could get started. And they do that with lots of other components within Facebook also. So, and if one day Messenger blows up, they can just take that part of the application, make it go away, scale it down to 0, and still have Facebook out there. So to support these different applications, we've got these basic patterns that application developers rely on. And one of the basic patterns is one that we've seen before, one that we're building for one of our labs, and that's a load balancer with many replicas. This is our, is it lab 2? Lab 3, I think it is. Lab 3, where we've got this load balancer out there, and then we've got 3 or 4 web servers that are all the same. I have you change them a little bit so we can tell which one is serving, but basically they're all the same. And that's this idea of having one load balancer in front of a bunch of back-end servers that are all the same. Users can access any one of them, receive the same information. So this is a common pattern. Another common pattern is single server with multiple backends. So in this case, we've got a single server that connects to a bunch of services that exist on other servers behind that single server. So from our perspective, I will have talked about this as a web server out in front that connects to a bunch of services in the back. An advertising service is a classic example. So if you use Google Ads, what you'll see is that Google Ads is a separate part of the Google world. And Google Ads exists in and of itself. So when your server comes in and requests files off of some web services or something in the Google world, it'll send a request out to the Google Ads, and eventually Google Ads will respond with the ads that they would like for you to serve. But it's totally different. Another great example of this is spell check. If you had multiple applications residing in one cloud-based environment, would you want to build a separate spell checking engine for each one of those? And the answer is, of course not. That's the dumbest thing in the world. So what you do is you build one spell check engine and then deploy that on all of the services where you need a spell checker. And so this multiple back ends is just a way to break up the traffic across multiple servers and take our big application and break it into multiple individual services. And this last one is a server tree, where we have a root branch of the server tree and then it branches down. Now, the classic example for this application pattern is search, where we search, have a request for a search come in at the root, and then we break it up into different components, and then break that into other components and other components and other components until we finally get to the results that we're looking for. So these three patterns are really important to understand when you start building, addressing, pretty much any kind of issue out there. Now, when we start breaking things up again, there's a few things that you have to remember, because these metrics are really important, and not in a physical fashion, but in a conceptual fashion. So you need to know things like an L1 cache reference is really fast. And so anytime you need something really fast, can you stick it in the cache? But on the other hand, if you're sending a packet from California to the Netherlands, and Netherlands to California, that's going to be really slow, 150 milliseconds. Well, if that goes back and forth twice, that's 300 milliseconds. If it goes back and forth, three times, you're at almost a full second. So, having a protocol that is chatty, it sends requests back and forth, back and forth, back and forth, that kills you in terms of the speed the speed of your application. So, and then other things we have in here, L2 cache reference. It's only 7 nanoseconds, but in L1 it was only half a nanosecond. So that's what, 14 L1 cache references equal 1 L2 cache reference. So, that's a lot slower. And then a main memory reference, a reference that goes to RAM, it's 100 nanoseconds. So, that's really, really, really fast. But, you just need to keep track of this stuff. Round trip within the same data center, 500,000 nanoseconds, or half a millisecond. So these things are just things to keep in mind as you start building applications and keeping track of why you'd want to distribute your application to different data centers around the globe. Why? You're avoiding the 150 millisecond round trip time. So that's where a lot of the cloud architectures come from. Why does Amazon have data centers all around the globe? Because of that. There's nothing you can do to avoid that. So what we really need is this: we need elasticity for our applications, supported by our architectures, our application architectures. But the problem is that that's hard to build unless you're using a cloud. So if you look at the predicted demand versus the actual demand, okay, so you're bringing up a new application, you're not really sure what's gonna, how much demand that application's gonna have. What do? Well, you start with a predicted demand. Somebody from marketing tells you, this is what we expect in terms of demand for this new application. And that's a nice, even keel. So, over time, the load on our application goes up. Excellent. As does the cost. But that's okay because we have more users using the application. But that's not the way our actual demand is going to work out. Our actual demand, the red line, is swoopy and curvy and everything. And that just shows the way applications go. At first, we have no users. But then over time, we start to get more users and it picks up pretty good and we're all excited. And then all of a sudden, for some reason or other, the load on our application goes down and we're oh no, chewing our fingernails, and then it goes back up again. We say, hey, it's going back up. And then we hit another peak and it goes back down, and so on and so forth. That's just reality for a new application. Um, but how do we build the hardware and resources to support that? Well, that's our traditional scale out approach, that green dashed line. So when we start a new application, we're going to allocate server resources to it. Why? Because we have to. And we're going to do that pretty flat. We're going to say this server is for this application, and we're going to leave it. And our demand for that application is going to go up. And it's skyrocketing, and we're thinking, oh no, we better get more servers in there. So we load some more servers on there, and then it's another flat point again. And our demand for the application goes down; it doesn't go up. Oh no, and so on and so forth. So we're continually allocating resources in the hopes that we can beat the growth and the demand for the application. But what that leads to are these huge capital expenditures at different points along the path, and those capital expenditures are tough to justify. They're hard to do accurately, and sometimes they're hard to do fast enough. So that's what we eventually we get to a point where we can't keep up with the growth in the application, and we get that little triangle at the top there where it says you just lost your customers. The reason that is because web users are notoriously impatient, and if we can't scale up our hardware fast enough to support the demand that our new application has, users are not going to be forgiving of a slow application. They're going to go away and go someplace else. So what do we need? We need elasticity. We need to quickly be able to add more capacity when we need it. And when we don't need it, it would be nice if we could take it away. In knowing that we could add it back if we needed to. So that green line is really where we would want to be, but it's just hard to do that by using an owned architecture, an architecture that we own. But if you do things in a cloud where somebody else owns the cloud resources, then you can allocate resources in line with your needs. Now, you'll also notice that the green line is above the red line. How come? Well, this represents the speed, the time that it takes to spin up new resources when you need them. You can't just instantaneously turn on new servers if that's when your workload goes up. It takes time for those servers to spin up, to look around themselves, see what resources they need to work with, connect into all those resources. All of that stuff takes time. And so we always want to spin up more resources before we need them. And that way they're ready and have merged themselves into the overall application architecture prior to their actually being needed. So I hope this little lecture about architectures helped you out a little bit. Uh, Fascinating stuff. World belongs to microservices and at least in parts of our applications. Not everywhere, but definitely in parts. So take care, everybody. See you later.